Okay, I think I told you that I will do some more, but I think it's enough now. We will do some more little later, right? Uh, so I'm now coming to continuous random variables and their distributions. So here we are going to learn some models again for the distributions of continuous random variables. So as we have discussed earlier, continuous random variable is a variable which takes any value in a given interval usually, right? So that is the main difference between continuous and discrete. Discrete random variable takes only a countable set of values. Usually there are gaps between those possible values. But in the continuous random variable, the random variable can take any value in a given interval generally, right? So for the discrete random variables, we discuss about mainly two probability functions. One is the probability mass function, right, which gives you the probability for each possible value separately, right? And then we discuss about the cumulative distribution function, capital Fx. That is the probability x less than or equal to some value x. So PMF is usually denoted by Pxx. That is the probability that x is equal to simple x. And the other one is cumulative distribution function, which usually denotes as capital Fx at some value x. This is the probability x less than or equal to x. So for this, for the discrete case. For the continuous case, there's a difference, because for a continuous random variable, we cannot have a probability mass function. Probability mass function is a discrete function. It gives you the probability for each possible value, where those values are the values that x can take, right? So x can take some discrete set of values only. But for a continuous random variable, as I mentioned, it takes all the possible values in a given interval. Therefore, that set is not countable, right? It's not countable. It's infinite, uncountable, right? Uh, so, Tenisa, there should be some continuous function for the continuous random variables, right? You cannot have a probability mass function. How do we just argue that continuous random variable cannot have a probability mass function? We can argue like this by using, for example, contradiction or negation. We can discuss like this. Suppose, for example, a continuous random variable has a probability mass function. Suppose it has a probability mass function. If it has a probability mass function, then it should satisfy some properties, because the probability mass function is defined by some properties, right? What are those properties? Sum of the probability mass function for each possible value should be equal to 1. That is one main requirement. But if, for example, a continuous random variable has a probability mass function, say, for example, Px, then that function also should satisfy that property, right? Sum over all possible x's, right? Pxx should be equal to 1 for all possible x's, where this goes over summation. But this will not be meaningful if x is continuous. Why? Because the set of possible values is not a countable set. It's a uncountable infinite set. In that case, the summation is not meaningful. Summation is not meaningful. Therefore, this kind of property cannot happen for that. So therefore, a PMF, probability mass function, cannot exist for a continuous random variable. So that is a very simple argument like that. So there should be some other function, but still we need some function to calculate the probability and so on. To describe the probability distribution, we need some function. but a mass function is not possible. So what we need is actually, instead of a summation, if we can find out some function, say fx, where integration over the set of all possible interval, right? For the whole interval, say s is equal to 1. That's what we have to do for a continuous random variable. Instead of this property, we have to look at a property like this, and we have to find out some fx which will give you value 1 when it is integrated over a certain interval, right? Interval is the set of values that x can take, right? So can we find out this kind of function is a problem, right? That is the problem. Can we find out that kind of function always? Yes, actually we can find out that kind of function like this. For a continuous random variable also, we can, even though we cannot define this function, we can define this function always. This function can be defined by this definition for continuous and discrete always, right? Only thing is that if you remember this cumulative distribution function for a discrete random variable is a step function. It is a step function going to 1 at the end, right? For the discrete. But for a continuous random variable, this is always going to be a fx is going to be a non-decreasing function, non-decreasing continuous function, right? So always for a continuous distribution function, this function exists, and it is like this, non-decreasing, and it's converging to 1 between 0 and 1. Right. So this function always exists, and using this function, we can find out a function like this. And that is what we are going to use instead of Pxx when x is continuous. Right. So how do we, using this function, how do we get a function like this? Now, because this function will be in general a differentiable function. So differentiable function, we can define the we can differentiate it. Suppose, for example, for at a given x, this function is differentiable, right? And then let's define the derivative of x. If it is differentiable at x, then derivative x is, and let us denote that derivative by fxx. Derivative x is, and let's call that a new value, right? Derivative is the slope of the function at x. No? So this function has some slope at each point, and if you get the slope at each point, you will have a new function. Let's call that function fx, and we can show that this function actually satisfies this condition. That is one thing, and it also that function is always greater than or equal to 0. And also we can show that by definition of this thing, by if you use this function and this definition, we can show that if you integrate this function over some restricted interval, then you will get the probability that x will be in that interval, right? Suppose, for example, there is a random variable in general, it is between say a and b, right? So in that case, the integration of this fx from a to b should be 1, right? That is one requirement for the density function. The other requirement is it should be greater than or equal to 0 for all x, and that will be satisfied also if you take fx to be this definition. And then if you consider any subset, say set a, then the probability that x belongs to a should be equal to the integration of fxx dx over this set a, right? That also should satisfy, and we can show that using these two, we can show that this actually satisfies, right? So therefore, what we take instead of the probability mass function that we have for a discrete random variable is the density function. This is called the probability density function. So for the continuous random variable, what we discuss is the probability density function. So there are two different things. right? Probability mass function gives you directly the probability of any value, any x value. But simple fx doesn't give you a probability, right? If you want to get a probability that x is in an interval, you will have to integrate this function, right? Fx doesn't give you a probability, but it is a probability density. It's called density. I'll later on explain why it is called density. Actually, from here also I can now itself I can explain why it is called density, because this is the derivative. Now you know how if what is the derivative of a function? Derivative is equal to fx, say x plus h minus fx divided by h when the limit h goes to 0. That's how we define a derivative, right? So if you look at this, what is this? This is the limit h goes to 0. What is this? This is the probability that x less than or equal to x plus h. And this is the probability that x less than or equal to x. So divided by h. Now what is this? This is the probability x less than or equal to h. Right. So suppose this x is somewhere here, and then x plus h is this. We are considering this interval here. So the probability x less than or equal to h, that is the probability that exists in this interval up to infinity or whatever a starting point, and then probability x less than or equal to x is the probability that exists in this interval. So this will give you that exists in this short interval, the probability that exists in that interval. So when you divide that by h, you get the probability divided by the length. So that's what you call the density, probability density, right? And what you look at is actually what happens if h goes to 0. So it's a probability density at a point. It's a probability density. So that's why we call it a probability density function. It's not a probability, it's a density at a given point, because we are dividing by h. Right? Okay, so by that argument, we can understand now for a discrete random variable, we usually talk about a probability mass function and a cumulative distribution function. For a continuous random variable, we talk about a probability density function and a cumulative distribution function. So let's look at some shapes of this probability density function. As I told you, the cumulative distribution function is always a non-decreasing function between 0 and 1. The value is, because it's a probability, always it has to be, because cumulative distribution function is probability x less than or equal to simple x. It's a probability, so it must be between 0 and 1. So it has this function because it's probability adding, we are adding, right? Therefore it cannot be decreasing, right? At some point it may be the same value, therefore some probability 0 in the interval, then the next value will be the same. That's why it can be like this, but it will never go down, right? So it's a non-decreasing function. Generally any continuous random variable will have this kind of shape for a cumulative distribution function. Right? If you take the derivative of this function, this is the curve that you get, derivative. Right? So therefore, for this CDF, this is the probability density function. Right? If the CDF can be like this also, so this is also a non-decreasing function. The cumulative distribution function is like that, then the density function will be like this, derivative of this function. If the cumulative distribution function is like this, then the density function will be like this, the derivative, right? So those are some possibilities. So what we are going to use is actually if some functions either like this or like this or like this as density functions. Right? So what we are going to do is actually for a given random variable, generally in order to find out probabilities and so on, what we do is we select a suitable probability density function model. There are so many mathematical functions with these shapes. No, there are mathematical equations with this shape, right? There are mathematical equations that has this kind of shapes also, right? You yourself can produce that kind of functions, right? So there are so many mathematical functions that people have created to get this different type of shapes like this. So for a given random variable with some data, if you have a reasonable amount of data, you can draw the histogram of those data, and then you can look at the shape of that histogram. What kind of shape in general will fit that, right? So depending on that, you can decide what mathematical model will be suitable for that shape. Right? Sometimes there can be several models which has this roughly the same shape. So in that kind of situations, we try several criteria to select the best model. We will discuss about those things later, right? So that's what we do, right? So there are different something called probability density functions, models defined by mathematicians, right? They have names, like one name is a uniform distribution, another name is normal distribution, another name is gamma distribution, another name is exponential distribution, Pareto, Weibull, log normal, and so many thousands of models are there with different shapes, gamma, beta, and so on. So generally we have an idea about what the shapes of those distributions are. So in a practical situation, if you want to deal with some probabilities and so on, what we do is we first of all look at the histogram of those data, and then by looking at that, we choose a suitable model from out of the models, that mathematical models we know, and then assume that X has that distribution, whatever, right? For example, if the histogram is a kind of bell shape, then one suitable model is the normal model, normal distribution. So we assume that X has a normal distribution. And then the mathematicians know, we know mathematical properties of that normal distribution, because that was defined by mathematicians. So there we know the mathematical properties of that distribution. So we can use the mathematical properties of those distributions to answer our questions. So that's the idea. That's the method that we will be using, right? So therefore, now I will introduce you some of the commonly used models for the probability density functions. Right? Commonly used models for probability density functions. Before that, now as I told you, once you select some suitable model, now we assume that X has that whatever that distribution. Then, if you want to find out the probability regarding that, as I mentioned, probability will be given by always the integration of the density function, right? Not the value of the density function at a particular X value, right? Usually for a continuous random variable, we are interested in the probability that X is in a certain interval rather than at a point, right? So if you are suppose you have selected the model like this, you will have this kind of model if you are considering some kind of mixture distribution. Two distributions mixed in a certain proportion can have this kind of shape. So suppose once you have decided on the model that you are going to use, then you can find out the probability that exists between any given two values, say these two values, by integrating that density function over that particular interval, right? So you know when you integrate a function, you get the area under the curve, right? So therefore, when you are dealing with continuous random variables, actually the probability is always going to be area under some curve, area under some probability density function, right? So therefore, always that's the way. But then remember that, so you can say probability that exists between C and D, for example, is going to be the integration of the density function from C to D. right? So say the CD, for example, the whole range may be AB. In that case, the whole integration from A to B should be equal to 1. That is one important property that density function should have. But then if it is satisfying that property, then the probability will be given by the probability in a given interval will be equal to the integration over that interval. Okay, so according to that definition, what will be the probability that x equal to a particular value? X equal to a particular value if x is continuous, right? This one I can write down like this. Probability x equal to simple x is the same as x is between x and x. It's the same, right? But what is this? How do you get that one? In order to get this one, you have to integrate the density function from x to x. If you integrate the density function from x to x, the answer is 0. So therefore, for a continuous random variable, the probability that x is equal to some value is always 0. Always 0. Which is not the same case for the discrete random variable. Discrete random variable, there can be a value, non-zero value for a x equal to some value. For a continuous random variable, always the probability x equal to something is 0. Right. So that's therefore for a continuous random variable, we are not really interested in the finding the probability that x equal to some value. Instead, in almost all the problems, we are interested in the probability that x is between some two values, or maybe greater than some value, or less than some value, and so on, not equal to some. So because of this property, for a continuous random variable, if you find out the probability that x be greater than c but less than d, only the greater than sign, it will be the same as even if you have equal sign here. Right? It will be the same even if you have equal sign here. It will be the same if you have equal sign in both places, because equal probability of being equal is 0, right? So therefore, when you are dealing with a continuous random variable, whether you talk about equality, whether your expression has equality or not is not important. It's immaterial, right? The answer will be the same, which is not the same, which is it's going to be very important in a discrete case, whether you have these two will get maybe quite different answers, and these two may get different answers, these two may be different in a discrete case. So that is one thing that you have to remember. Right. So as I mentioned, now we are going to look at some commonly used models, right? So there are so many different shapes that people have created mathematically. There are so many different distributions. I have shown you here a few of those, right? Some of them now one thing important here is if you mathematically explain about this thing, the area under any of these curve, or each of these curve is equal to 1, the total area, because they all are density functions, right? So the area under this curve is the same as area under this curve. It is the same as area under this curve. So 1 always, right? So you can see that there's a this one is called uniform distribution. This is something called a beta distribution. There is a one called normal distribution, another one called T distribution, another one called Cauchy distribution, and so on. So we are going to learn some of them and their properties now. Now, when we talk about distributions, actually, we usually once you want to find out a model, as I mentioned earlier, what we usually do is we collect some data for that random variable. Usually, you have to have a reasonable number. You cannot have get a idea about the shape using 20 or 30 observations, because the histogram will not be clear enough. But if you have about 100 observations, then you can get a rough idea about the actual shape of the density function, because histogram with a large number of observations will have the same shape as the suitable density function, right? So therefore, get as many as observations, and then draw a histogram to get a idea about the actual shape of the probability density function for that random variable. And then out of select one of the suitable mathematical models from all the models out there, maybe you can first select 2 or 3 models and then choose the best one out of those. Right. But when we talk about these distributions, for example, we actually talk about families of distributions, not a single distribution. Family. We talk about a normal family, gamma family, right? And then beta family and so on. Because we have already discussed about the normal distribution, I will talk about this normal family now. So when we write down the density function of us for a certain random variable, usually we write down with something called parameters. So the density function for the normal family will be like this: 1 over root 2 pi sigma e to the power minus half x minus mu over sigma square. Right, so here the variable, mathematical variable is x, but in addition to that, you can see that in this particular mathematical equation, there is something called sigma, there is something called mu. Right? In this case, this mu has to be any value between minus infinity and plus infinity. Sigma has to be greater than or equal to 0. So now, by changing x with a fixed value for mu in this range and a fixed value of sigma in this range, we can get one member of this family. So this one actually a family, right? If, for example, if you have 10 here and then sigma is equal to 3 and 3 here, this gives you one member of the normal family. Right? If you have 15 here and 6 here and then 6 here, that is another, that gives you another member of the normal family. Right? So therefore, usually we talk about a family of distribution. So within a family, there can be large number of possible members. So in a particular situation, what we have, if you think that, okay, our histogram has a normal shape is generally called the bell shape. So if your histogram is roughly a bell shape, you first get the idea, okay, one member of the normal family may be suitable for this as a model for this case. Now you first identify the family, right? Because you generally know what are the shapes of the distributions in that family. And then it comes, what are the values suitable for mu and sigma for our particular situation. Right? So those values are called parameters. Generally, in the beginning stage, we don't know the values. There can be some value for mu and some value for sigma. The question is our particular problem. What is the most suitable value for mu and what is the most suitable value for sigma? So there we have to estimate some values for mu and put there, and then use that function for the further calculations. So therefore, in general, when we talk about the distributions, models, there are parameters in those functions. Right? In this one, mu and sigma are parameters. There is another density function like this, lambda e to the power minus lambda x. Right? So this is a function of x, but there is a one parameter, lambda. There is another function like this, and so this has two parameters, beta and alpha. So this gives you whole family. This gives you a whole family. In this case, there is a restriction that lambda has to be greater than 0 and so on. Right. So these parameters, usually when we talk about these distributions families, we use some words to describe these parameters, different types of parameters. Some parameters called location parameters. Location parameters. Some parameters called scale parameters. Some are called shape parameters. Right? So I thought it's better to give you a rough idea about how to distinguish between these parameters. Right? That's additional knowledge actually. These are not in book, but it's better to know something about this. Why are we using different names for this? So one is the location parameter, the other one is the scale and the shape, right? Now the location parameter actually, if you change the location parameter, what happens is the whole distribution will shift. Change the location only. It doesn't change the shape, right? For example, when mu is equal, in this one mu is equal to 10, the distribution will be symmetric around value 10. If mu is equal to 15, now the whole distribution will be shifted and it will be symmetric around 15. So in general, therefore, the location parameter gives you the general location of the distribution. In that case, it is actually shifting the distribution along the x-axis. And then this parameter and this parameter are called scale parameters. ඒකෙන් කරන්නේ scale parameters actually changing the scale of the distribution. එතකොට ඒකෙන් කරන්නේ variability එක වෙනස් කරන්නේ බොහෝ වෙලාවට. Right? When you change sigma, either the distribution will be very flat or slim. Right? It usually controls the variability. The other type of parameters called shape parameters generally changes the other properties like skewness and kurtosis of the distribution. Right? So those are therefore different types. How to identify whether a given parameter is a location parameter and whether a given one is a scale parameter or the shape parameter, I can give you a rough idea. These are not definitions, but in general, if you have in your density function, if you have something like x minus something, right, x minus or x plus something, then that quantity will be a location parameter in general. These are not rules. These are not always correct, but most of the times it will be a location parameter. If you change this one, the distribution will change its location. Right? If you have something like this, x divided by something, or x, this is the same as x multiplied by 1 over sigma, right? Or x times some k, right? X divided by or x multiplied by something in the density function, usually that gives you a scale parameter. That kind of parameter is called a scale parameter. Right? There are situations where the density function has some power, x to the power 2, right? Like the density function that I wrote earlier, fx equal to e to the power minus x over beta, x alpha minus 1, gamma alpha and beta alpha. So here you have x over beta. So this beta is a scale parameter. And there's a power here, x to the power something. So this alpha is a shape parameter. When you have power type quantity, it's called a shape parameter, right? We are looking at with the x, how does it look, right? So like that, there are three different types of parameters. මොකද හුඟක් වෙලාවට මිනිස්සු නිකන් ඔහෙ කියනවා මේක shape parameter මේක කියලා. ඒකට කට්ටියකට සමහරට පැටලෙන්න පුළුවන්. ඒකයි මම මේ idea එක දුන්නේ. තියෙන්න පුළුවන්. ඒ අපිට හදන්න පුළුවන්. ඔයාට හදන්න පුළුවන්. හදලා ඔයාගේ නම දාගන්නත් පුළුවන්. ඔව්. තුනම දාන්න පුළුවන්. ලේසියෙන් වෙනස් කරන්න පුළුවන්. දැන් මේක මෙතන x තියෙන එකට මට මේක මෙතන හදන්න පුළුවන්. මෙතන x minus some k වල alpha minus 1. මෙතන x minus k divided by beta කියලා හදන්න පුළුවන්. මම හදන්න පුළුවන්. ඒතකොට තව පැරාමීටර් එකක් ඇඩ් කරා මම ලොකේෂන්. හැබැයි එකම දේ වෙන්නේ මේකේ ඉන්ටග්‍රේෂන් එක එක වෙන්න ඕන. ඒතකොට ඒක එක වෙන්න නම් සමහර වෙලාවට මේක යම්කිසි ගානකින් තව වැඩි කරන්න වෙන්න පුළුවන් අපිට. නැත්නම් බෙදන්න වෙන්න පුළුවන්. මොකද මේ මෙතන මේ අනුකලනය ඉස්සෙල්ලා අනුකලනය දෙකම සමාන නැහැ. ඒතර මේකට එන උත්තරේ එක කරගන්න අපිට එක ස්කේල් කරන්න වෙනවා. මේක ඩෙන්සිටි එක හදාගන්න පුළුවන්. right? මේ ඔක්කොම මිනිස්සු හදපුවා තියෙන ඩෙන්සිටි ෆන්ක්ෂන්ස් right. දැන් හදන ඒවා මම දැක්ක කුමාරස්වාමි ඩිස්ට්‍රිබියුෂන් කියලා එකක් තියෙනවා. පෙරෑටෝ ඒ ඔක්කොම නම් දාපුවනේ. එක එක්කෙනාගේ නන්නේ තියෙන හුඟක් වෙලාවට අලුතෙන් හදන ඒවා. පෙරෑටෝ ඩිස්ට්‍රිබියුෂන්, කුමාරස්වාමි ඩිස්ට්‍රිබියුෂන්, තව එක එකව තියෙනවා. ඈ? ෆිසික්ස් වල තියෙනවා ගිවින් ඩිස්ට්‍රිබියුෂන්. ඔව්. එහෙම තියෙනවා. right. So those are the types of parameters. I have some notes here. Okay, so now let's look at some commonly used models. The first one is the uniform distribution. So, for example, suppose you draw a histogram of about 100 observations and you see roughly this kind of shape, not exactly like this. Then one first idea that comes to your mind might be, okay, maybe your uniform model is suitable in this case, uniform distribution. Right. So for the uniform distribution, you have to specify what is the first, the smallest value and the largest value. We say uniform between A and B, uniform distribution. Right. So that's then if it is a picture like this, you know that the area under the curve should be 1. So thereby you can easily define, see that the height of this thing should be 1 over b minus a. Then only the area will be equal to 1. So therefore the density function for a uniform distribution between a and b will be given by 1 over b minus a. Right? It's a fixed value in a given area. Height is equal to this. So that's the equation for the uniform density function. Uniform density function of a uniform distribution. මතක තියාගන්න ඕන දේ තමයි මෙහෙම මෙව ඇවිල්ලා models. In real life, there are no situations where exactly random variable has a uniform or exactly normal or exactly something. Right? These are only going to be approximate some actual distributions, approximating. Right? But for most of the purposes, if your selection of the model is suitable enough, then final answer that you are looking at will be good enough. Right. So uniform distribution like that. So for in order to use that thing, you have to know the value of a and b. Right. So naturally you will take the minimum of your data as an estimate for a, maximum of your data as the estimate for b. Naturally, that is the, because all the data are between a and b, therefore the model should also be between a and b. Right. So that's how you decide. So here I have a very simple example where you can use the normal model. The time interval in minutes between two consecutive defective light bulbs from a production line has been measured for 300 occurrences. The following figure shows. So මෙතන observations 300ක් තියෙනවා. මොනවද variable එක? එක defective bulb එකක් ආපු වෙලාව ඉඳලා අනිත් defective bulb එක එළියට එනකන් production process එක කාලය මැනලා තියෙනවා. ඒ කියන්නේ හැමතිස්සෙම කාලයම අයින්නවා. අර අන්තිමට හොයා ගන්නවා defective bulbs. හැම එකම check කරන්න වෙනවා. ඒතකොට check කරනකොට defective bulbs දෙකක් අතර කාලය. ඊට පස්සේ ආයෙසරයක් defective ඒකයි ඊළඟ එකයි අතර කාලය. එකයි ඊළඟ defective bulb එකයි අතර කාලය. ওই විදිහට මැනපුවාම යම්කිසි observations ටිකක් ආවා. So we don't know what the suitable model for that. So we know that there are some values. සංඛ්‍යා දිහා බලලා අපිට model එක හොයාගන්න බෑ. සංඛ්‍යා, if you just inspect the numbers, it's difficult to think about a suitable model. But if you draw the histogram, you will be able to. For example, in this case, when they draw the histogram, it looked like this. Right? එතකොට the most close model out of the known distributions for this is actually the uniform distribution. Right? So therefore, we will generally assume that X has a uniform distribution. When you say X has a distribution, uniform distribution, it doesn't mean the actual distribution is exactly a uniform distribution. That's only a model. Right? So you have to find out, say, okay, uniform what? Uniform, when you say uniform, again, there is a family of uniform distributions. A සහ B වෙනස් කරන්න when you change A and B, you will get different members of that family. So the question is, for this particular example, what member will be the best model, right? So in this case, the minimum value was 0, the maximum value was 90. Therefore, for the data, right? And therefore, it's reasonable to assume that X has a uniform distribution between 0 and 90 as the model, right? Okay, so that's the simplest model that you can think of. Here I have written down some other situations. I have already given you one example. Some other situations where the uniform model might be suitable. Right? For example, if a defect is equally likely to occur anywhere along a production line, length L a line of length L, its location can be modeled as right. එතකොට දැන් මොකක් හරි අපි හිතමු මොකක් හරි is anywhere along a production line of length L, its location can be modeled as again, if a defect is equally likely to occur anywhere along a production line of L length. නෑ මෙතන production line නෙමෙයි. යම්කිසි product එකක් වෙන්න ඕන. යම්කිසි L දිග තියෙන product එකක අපි හිතමු දැන් මයින්නවා යම්කිසි starting point එකක් තියෙනවා end point එකක් තියෙනවා. අපි හිතමු මොකක් road එකක් කියලා. ඒතර road එකේ දිග L. ඒතර ඒකේ ඕන තැනක පොඩි dot එකක් වගේ දෙයක් තියෙන්න පුළුවන්, defect එකක් තියෙන්න පුළුවන්. ඒතර මෙතන ඉඳලා ඒ defect එක තියෙන තැනට තියෙන දුර ගත්තොත් අපි variable එකක් විදියට ඒක ඕන තැනක තියෙන්න පුළුවන්. සමහරට ඒක තියෙන්න පුළුවන් probability එක සමානයි. මේක තුල uniformly distribute වෙලා තියෙන්න පුළුවන් ඒ තියෙන තැන. එහෙම වුණොත් අපිට ගන්න පුළුවන් the location L from the starting point of the rod will be uniformly distributed. Okay, one example. ඊට පස්සේ another one මෙතන තියෙනවා, suppose a measurement is rounded to the nearest unit, the rounding error is between -0.5 and +0.5. අපි යම්කිසි අපි හිතමු නොදන්නා බරක් මයින්නවා, නොදන්නා දෙයක දිග හරි බරක් හරි මයින්නවා කියලා හිතමු. එතකොට එක එක්කෙනාට මයින්කොට එන error එකක් තියෙනවා. හැමෝටම එකම වගේ එන්නේ නැහැ. right? එතකොට එන දශම ගණන් තියෙන ඒවා අපි බැලුවොත් එහෙම රවුන්ඩ් කරොත් එහෙම right? දශම යම්කිසි එකක් එක දශම 5ට මේ පැත්තේ තියෙන එකක් නම් අඩු නම් අපි මෙහා පැත්තේ අගයට ගන්නවා. 14.4 තිබුණොත් 14 විදියට ගන්නවා. 14.6 තිබුණොත් 15 විදියට ගන්නවානේ. එතකොට ඇත්තාගේ 17 මේ අපි ලියාගන්නේ 14 කියලා තමයි රෙකෝඩ් කරන්නේ. එතකොට error එක වෙන්නේ අර ඔබ්සර්වේෂන් එකෙන් 14 අඩු කරපුවාම එන්නේ. එතකොට මේ විදිහට විවිධ ඔබ්සර්වේෂන්ස් වල errors ගත්තාම ඒව තියෙන්න පුළුවන් ඍණ 0.5 සහ ධන 0.5 අතර ඕනම අගයක් වෙන්න පුළුවන්. එතකොට ඒ වගේ වෙලාවට මේ measurement error එකේ rounding off error එක ගත්තොත් එහෙම ඒකත් uniform කියලා ගන්න පුළුවන් සමහරවිට. Suppose a machine operates continuously in and inspection time is chosen randomly within a fixed interval. අපි හිතමු යම්කිසි නිෂ්පාදන production process එකදී they have to carry out some inspections, right? උදේ 8යි හවස 4යි අතර ඕනම වෙලාවක inspection එක තෝරගන්න පුළුවන්. ඒතර inspection එක තෝරගන්නේ වෙලාව විශේෂ එකක් නැතුව randomly තෝරගන්නවා නම් එතකොට ඒකත් තෝරගන්න අවස්ථාව uniformly කියලා ගන්න. ඒ වගේ practically that there are not so many situations, but there are situations like that where you can use the uniform distribution. Theoretically also uniform distribution is suitable, because if you look at we will probably talk about this thing later. If you consider any continuous random variable x, then fxx අපි හිතමු x තියෙනවා, ඊට පස්සේ අපිට දත්ත ටිකක් තියෙනවා x1 x2 ආදී වශයෙන් xn දක්වා. fxx2 and so on fxxn. These values will have a uniform distribution, right? So that's a theoretical thing that we will need later on, right? If you have some observations from a continuous random variable, and if you calculate the cumulative distribution function at those values, then those values will be uniformly distribution between 0 and 1, because all these cumulative distribution functions are probabilities, right? This is the probability that the random variable is less than or equal to x1. This is the probability that random variable x is less than or equal to x2, and so on. So all those are between 0 and 1. Those will be uniformly distributed. We can write down our program and check that one also little later sometime. Right. So that's one model. So if you use R, there are built-in functions to calculate the probability for the uniform distribution and generate random numbers. So those functions are like in the previous one, random. When you want to generate random numbers, the words start with R. And then when you want to calculate the density function, if you want to calculate the density, it starts with D. The other one is the cumulative distribution function. It's starting with P. And if you want to find out a quantile, that is, for example, if you want to find out in this distribution, say 95th quantile. What is this value? So that this area is 0.95. This value here is called the 95th quantile. That can be found using Q. Right? So the functions are going to be R unif, D unif, P unif, and Q unif. So those are the R functions that you can use. So if you want to suppose that X has a uniform distribution, that you have decided that the minimum value is 10 and the maximum value is 20, and you want to find out the probability X less than 12, those days when you do manually, what you have to do is you have to first find out the density function. In this case, the density function will be 1 over b minus a, that is 20 minus 10, that is 0.1, when x is between 10 and 20. So what you have to do is, if you want to find out the probability that x less than 12, you will have to integrate 0.1 dx from 10 to 12. You have to integrate the density function in that region and then get it, right? Now, but we don't have to make an integrate කරන එක මහකට නෙමෙයි. නමුත් අර mathematical බර functions ආපුවම integrate කරන එක ලේසි වැඩක් නෙමෙයි. එතකොට මෙතනදිත් අපිට පුළුවන් p unif, right? So in order to calculate this one, the command will be p unif, cumulative distribution function p unif, at 12, and then you have to give the two values a and b. A is equal to 10, b is equal to 20. Right. So that's how you get the probability x less than or equal to 12 of a uniform 10-20 distribution. Right. So you can get the other values like that also. Normal distribution එක ගැන ගොඩාක් දේවල් කියන්න තියෙනවා. ඒකෙන්ද මම අද මෙතනින් නවත්තනවා. අනිත් දවසේ කතා කරමු normal distribution. Right.